So today we are going to learn about functions of several variables. So before coming to the things we are going to learn about functions of several variables, let me tell you why exactly we are interested in studying functions of several variables. Well, you must have noticed that even to draw curve given by a function, we need to know certain analytic facts about functions. For example, whether the derivatives of the function exist or not, to understand whether the curve is increasing, then the convexity, concavity, maxima, minima. With all these informations, sometime we can draw the curve of a function. So this is where calculus helps us understanding curve of a function. Now, suppose instead of curves, you are interested in surfaces. For example, I am interested in the sphere in 3 dimensions. So what is the equation? It is collection of all x, y, z such that x square plus y square plus z square equal to some constant, where a is a constant, is a real constant, that is, it's a real number. Now this is a sphere centered at origin with radius a. Now this can actually be understood in terms of certain functions. So if I define f of x, y, z equal to x square plus y square plus z square, then if I call this s, then s can also be written as all x, y, z such that f of x, y, z is equal to a. So with this surface, there is naturally associated a function. The surface in some sense comes out of the function. So if you really want to understand this surface properly, the geometric properties of this surface, one way is to look at the function which produces it and try to understand the function. So this is a big motivation for studying functions of several variables. So what exactly is a function of several variables? So let me start with functions of two variables. So let us say D is a subset of R2. What is R2? R2 is the set of points of the form xy, where x is a real number, y is a real number. Okay. Usually we try to draw R2 in this form. There are two axes. One is called the x-axis, other is the y-axis. And if this point I want to say is xy, that means this distance is x and this distance is y. Okay. Now, if I have a function f from D to R, then f is a function of two variables, namely x and y. It will be more clear if I look at examples. Let me take D to be equal to R2. So I am going to talk about a function f defined from R2 to R. That means I take a point in R2 and f of that point should be a real number. So I can define f of xy equal to 1 for all xy in R2. This is certainly a function of two variables, a constant function. I can also define f1 of xy to be equal to, what can you do with two real numbers? Well, you can add them, so you define this. f1 of xy is just x plus y. Similarly, I can define f2 of xy equal to x minus y. I can also define f3 of xy equal to x times y. What I mean is the multiplication of two real numbers. I can define f4 of xy x by y if I like, with y not equal to 0, and so on. So given x and y, there must be some rule which tells me what real number I get out of xy. That is a function of several variables. Now what do we really want to study about functions of several variables? So we will try to have analogues of what we have done for one variable functions. So what did we do? We first looked at sequences. So xn converges to x. That was a very fundamental notion. Using that we could talk about limit, continuity and such things. And then finally differentiability, maxima, minima, integrals. Now I want to do all these things with functions of two variables. So here the most fundamental thing to start with is, like real variable case, the convergence of sequences. So what is a sequence here? Well, it's exactly analogous to one variable. I look at xn, yn, where n belongs to the set of natural numbers. This is a sequence, but it's a sequence of two variables. So to give an example, I can define 1 by n, 1 by n square. This is a sequence of two variables anyway. Here xn equal to 1 by n, yn equal to 1 by n square. I could have as well defined it as 1 by n, then 1 by m, where n and m both are natural numbers. So it's just a mix of two sequences of real variables. In the first coordinate you have one sequence, in the second coordinate I have another sequence. Coupled together, that gives me a sequence of two variables. And now I want to talk about convergence of these sequences. So let's go back to the definition. In the one variable case, what was it? I have a sequence xn. What does it mean to say xn converges to L as n goes to infinity? It means, so given epsilon bigger than 0, there exists a natural number n, it belongs to the set of natural numbers, such that modulus of xn minus L strictly less than epsilon if n is bigger than or equals to capital N. So that means if you fix epsilon bigger than 0, then if you take larger and larger n's, then the distance between xn and L becomes less than epsilon. Modulus of xn minus L just stands for the distance between xn and L. Here the key point is to generalize this notion of distance in the two variable case. Now in the two variable case, if I take a point xy and another point x1 y1, then there is a naturally defined distance between these two, the Cartesian distance, which we always use in the coordinate geometry. So what is the distance between this? So distance between the above points is square root of x minus x1 square plus y minus y1 square. It is a generalization of the notion of modulus, becomes very clear if I look at the point x0 and y0. Then the distance according to the above formula is square root of x minus y square. But since I am taking the positive square root, it is just modulus of x minus y. So in that sense, this distance, called the Euclidean distance between 2 points, is a generalization of modulus. So I am going to use this to define convergence of sequences. So I am going to use some notion for this, that the distance between xy and 0 0 is denoted by, it's called norm, a double modulus kind of. This is, by the above definition, is square root of x square plus y square. Okay, that means in this definition you just take x1 to be equal to 0 and y1 to be equal to 0. Then what you get is this. Now I say, now the definition, a sequence xn yn, since I am in R2, I have to talk about sequences where each element is a tuple. This converges to an element Lm in R2 if, you will see it is exactly analogous to the one-dimensional case, that given epsilon bigger than 0, there exists capital N such that for all n bigger than or equals to capital N, norm of xn yn minus Lm is less than epsilon. The only difference with the one-dimensional case here is that the modulus has been replaced by the norm. Now let us look at this definition closely again. I write down the quantity norm of xn minus L. I just write down this quantity xn yn minus Lm. I know what this means. It is square root of xn minus L whole square plus yn minus m whole square. Because of this, I immediately get that modulus of xn minus L, which is less than or equal to square root of xn minus L square plus yn minus m square, which is equal to norm of xn yn minus Lm. And the similar thing happens with modulus of yn minus m also, that this is also less or equal to norm of xn yn minus Lm. Now if little n is bigger than or equals to capital N, since norm of xn yn minus Lm is less than epsilon, it then follows that modulus of xn minus L is less than epsilon and modulus of yn minus m less than epsilon. So what I got is that given any epsilon bigger than 0, there exists a capital N such that if n is bigger than or equals to capital N, then modulus of xn minus L is less than epsilon, modulus of yn minus m is also less than epsilon. It means that xn converges to L and yn converges to m. So xn yn converges to Lm, that means if you concentrate on the first coordinate, that is if you get the x sequence xn, then xn converges to L. If you concentrate on the second coordinate, that is if you look at yns, then yns converge to m. What about the converse? That suppose xn converges to L and yn converges to m. So I will put it as a question. If xn converges to L and yn converges to m, is it true that xn yn converges to Lm? Fortunately, the answer is yes, and it can be proved as follows. So start with an epsilon. What is the job? The job is to get capital N such that for all n bigger than or equals to capital N, this should happen. This should be less than epsilon. Okay. Now, I already know that xn converges to L and yn converges to M. So what I do is get n1 and n2 such that xn minus L strictly less than epsilon by 2 root 2 for all n bigger than or equals to n1. Okay, and yn minus M less than epsilon by 2 root 2 for all n bigger than or equals to n2. That means here instead of epsilon, I am using epsilon by 2 root 2 in the definition of convergence xn converges to L. Now I look at norm of xn yn minus Lm. I have the definition of this, so it is square root of xn minus L whole square plus yn minus M whole square. If I assume my n is bigger than or equal to maximum of n1, n2, then what I get is that this is less than square root of half epsilon by 2 square plus half epsilon by 2 square. What I get is square root of epsilon by 2 whole square. So that is epsilon by 2, which is anyway strictly less than epsilon. This is then less than epsilon by root 2 square plus epsilon by root 2 square, which is square root of epsilon square by 2 plus epsilon square by 2, that is epsilon square, which is equal to epsilon as epsilon is positive. That means if I choose my n to be bigger than or equals to this capital N, then norm of xn yn minus Lm is less than epsilon. That precisely means that xn yn converges to Lm. So we understood something important here about convergence of sequences. What we got is, I will put it as a proposition. All it says is that a sequence xn yn converges to an element in R2, which I call Lm, if and only if xn converges to L and yn converges to M. Now because of this proposition, it becomes really easy to give examples of sequences in R2 which converges. All we have to do is we pick two convergent sequences xn and yn from real line and put them together as xn yn, and that is the only thing which you have to do to give examples of a sequence in R2 which converges to some Lm. Now given this, I can go to definition of continuous functions. So I start with continuous functions. Here we will not prove everything because things are very analogous to the one-dimensional case, but let me just go to the definitions and try to convince you that this is an analog of the one-dimensional case. So let us say f is a function. Let us start with from R2 to R. Suppose x0 y0 is a point in R2. What do we mean by f is continuous at x0 y0? Well, analogous to the one-dimensional case, I say one way of defining this is, it means if a sequence xn yn converges to x0 y0, then the sequence of real numbers f of xn yn converges to the real number f of x0 y0. This is exactly analogous to the definition of continuity on real line, that f is continuous at a point x0 if for every sequence xn, xn converges to x0 implies f of xn converges to f of x0. Okay. So this is one way of defining, but there is an alternative way of defining continuity using epsilon and delta exactly as it is on real line. So that is this, that given any epsilon bigger than 0, there exists delta bigger than 0 such that modulus of fxy minus f of x0 y0 is less than epsilon if, now instead of modulus I have to use norm, because in the case of real line I use modulus of x minus x0 because there the variables on which the function is defined are real numbers. The only reasonable notion of distance there is modulus. But here the variables on which the function is defined, they are elements of R2. So the only natural way to define the distance is to use the Euclidean distance. So here if the distance between xy and x0 y0 is less than delta. So these are two ways. Now what I want to do is I will try to see some simple examples of continuous functions by these two criteria. So we start with my example. Suppose I look at the function f of xy equal to x plus y. Okay, I want to see whether it is continuous at any point x0 y0. Choose a point arbitrarily. I want to check whether my function f is continuous at x0 y0 by the first criteria of continuity, that is through sequences. So I choose a sequence xn yn which converges to x0 y0. Then by my proposition I know that xn converges to x0, yn converges to y0. Now apply a result about sequences which we have proved long back, that if you have two sequences xn and yn such that xn converges to L, yn converges to M, then xn plus yn converges to L plus M. Now by that result this implies that xn plus yn converges to x0 plus y0. But then by the definition of the function it just means that f of xn yn, which is defined as xn plus yn, it converges to f of x0 y0. So this is by one criteria. Now the second one, given epsilon bigger than 0, to find delta bigger than 0 such that norm of xy minus x naught y naught less than delta should imply that modulus of fxy minus f of x naught y naught is less than epsilon. Okay. So given epsilon, I have to find a delta. So I start experimenting with modulus of fx y minus f of x naught y naught. This simply turns out to be modulus of x plus y minus x naught plus y naught, which is modulus of x minus x naught plus y minus y naught, which is anyway lesser equals to modulus of x minus x naught plus modulus of y minus y naught. Now I have observed then that this is lesser equal to square root of x minus x naught square plus y minus y naught square into 2, because look at this quantity. I have observed that this is lesser equal to square root of x minus x naught square plus y minus y naught square. Similar is the second quantity. So both of them are actually less than square root of x minus x naught square plus y minus y naught square. So as a whole, the whole thing is less than this. Okay. So I want to prove this to be less than epsilon. For which delta it should happen? Now the choice is obvious, because this quantity is nothing but 2 times norm of xy minus x naught y naught. I want this to be less than epsilon. That means norm of xy minus x naught y naught should be less than epsilon by 2. Choose this as delta. That gives me continuity of the function by the second criterion. But in many cases you will see it turns out that the first definition works, but in many other cases it is the second one which works. That's why I have given both the definitions. Depending on the problem, you use one of the criteria to check continuity of a function at a point. Now using this you can actually create more complicated continuous functions. For example, let us say f from R to R is continuous and g from R to R is continuous. Now I define a function capital F from R2 to R by the following rule, that f of xy equals to fx into gy. I can also define g of xy equal to fx plus gy. I say both the functions f and g are continuous functions. Now I will try to prove only that capital F is a continuous function. The proof of continuity of capital G I will leave as an exercise. So how do we prove that capital F is continuous function? I try to use the sequential criteria. So take a sequence xn yn converging to x naught y naught. This then implies that xn converges to x naught, yn converges to y naught. In fact, it is implies and implied by my proposition. Since little f and little g are continuous functions, I have that fxn converges to fx naught, gxn converges to gx naught. But then again, by a result on sequences, I get that fxn times gxn converges to fx naught times gx naught. But look at the definition of the function. This implies this is just f of xn yn, and this is f of x naught y naught. So by the sequential criteria, capital F is a continuous function. Exactly a similar kind of proof will tell you that capital G is also a continuous function. So this way you can create more complicated continuous functions of two variables using one-dimensional continuous functions. Let us see some more examples. Now let us look at another example. I define f from R2 to R given by f of xy equal to sine square of x minus y divided by mod x plus mod y if xy not equal to 0, 0. That is, for the non-zero points, the function is this. I define it to be 0 if xy equal to 0, 0. Question is f continuous? What I will do is, I will just check continuity of the function at 0. For other points, the function is certainly continuous, and that I leave as an exercise using the previous results. Now, why is this function continuous at 0, 0? For that, what I do is, I try to estimate this f of xy minus f of 0, 0. This, by the definition of the functions, is sine square x minus y divided by mod x plus mod y, because xy is not equal to 0, 0 here. Now, using the fact that sine x is lesser equal to x, I get that this is lesser equal to mod x minus y whole square divided by mod x plus mod y. That means, which is same as mod which is obviously lesser equals to mod x plus mod y, which then is lesser equal to which is same as so if you start with an epsilon bigger than 0, you want to make this less than epsilon for some choice of delta, then the obvious choice of delta is delta equal to epsilon by 2. So given any epsilon bigger than 0, I can find a delta so that mod of fx minus f00 is less than epsilon if norm of xy minus 0, 0 is less than delta. So that shows f is continuous at 0, 0. At other points which are not the point 0, 0, you can apply our example 2 to show that the function is continuous, because you can write then in terms of one-dimensional continuous functions. Okay? Fine. Let us go to another example. F of xy equals to xy by x square plus y square if xy is not the point 0, 0. At 0, 0, I define it to be 0. Is f continuous? Now, unless you have any guess about continuity of a function, it becomes a bit difficult to check whether the function is continuous at a point. Okay. So since I don't know, I will try to estimate xy by x square plus y square minus 0. So mod, I want to make this less than epsilon for some choice of delta. But this only thing what I can do is this xy is lesser equal to less than half x square plus y square with am bigger than or equal to gm, then it is x square plus y square. So I just get that it's half. I could not really make it small. So that seems there exists some problem here. Perhaps this function is not continuous. So what I do is since I have to converge to 0 to check continuity, the point 0, 0 is here. Okay, I can converge to 0, 0 through any line if I want. So I choose to converge to 0, 0 to come this way through the line y equal to x. So if I put y equal to x in the function, so fxx, that is x square by twice x square, which is equal to half. So if I take limit as x going to 0, I am again going to get half, which is not equal to f of 0, 0. Okay, so that means if I choose the sequence xn yn equal to 1 by n, 1 by n, then what happens is f of xn yn, I can easily calculate it. It is 1 by n square divided by 2 by n square, that is half. It does not converge to the value of the function f of 0, 0. So f is not continuous at 0, but that is not the end of the story. Suppose I change my value of the function at 0, 0 to be f of 0, 0 equal to half, and f of xy remains same. This is xy by x square plus y square. This is if xy not equal to 0, 0, and this is xy equal to 0, 0. What happens then? Well, in this case, I can try to approach 0, 0 through 2 by n. For example, I choose this sequence xn yn equals to, let us say, 1 by n, 2 by n. Then what is f of xn yn? That is 2 by n square divided by 3 by n square, which is 2/3. It's not equal to half again. Okay, and hence this does not converge to half. So in this case, whatever way you define f of 0, 0, you cannot make it continuous. This implies f is not continuous. The point is, if f is continuous at 0, 0, through whatever path you go to 0, 0, f of the values should converge to f of 0, 0. Now here what happens is, I got two paths. Pictorially if I look at, this is y equal to x, and then y equal to 2x. If I go through this path, the function is going to half, and if I go through this path, this goes to half, but this is going to 2/3. Those values are not same, hence the function cannot be continuous. So we have seen some examples of continuous functions as well as some examples of discontinuous functions also, and now we know how to create more complicated continuous functions starting from functions of one variable. Now with all these concepts, now we want to go towards differentiability of functions. Now we come to differentiation of functions. So how to define derivative of a function? Again we start trying with analogues of the one-dimensional case. So in the one-dimensional case, given a function f, we usually look at this quotient, limit h going to 0, f of x plus h minus fx by h. If this limit exists, we call it f prime at x, the derivative of f at the point x. Now here, if I start looking at the analog of this, I take a point x naught y naught and then try to have an analog of the previous one. So I can write this in this form, that f of x naught plus h, I don't do anything with y naught, I keep it fixed, minus f of x naught y naught, I divide this by h, I take limit as h going to 0. If this limit exists, I will like to say that f is differentiable at x naught y naught. It's not really doing justice to y naught that we can see immediately, but still this limit might exist. We call it del f del x at x naught y naught. Similarly, I can define limit h going to 0, f of x naught. Now I am going to play around with y naught. If this limit exists, I call it del f del y x naught y naught. I will also denote this sometime as f suffix x at x naught y naught, and the next one I will denote by f suffix y at x naught y naught. These are called partial derivatives. So fx, fy are called partial derivatives. Now to have an example of this, let me look at the function which I looked at before, fxy equal to xy by x square plus y square. When xy is not equal to 0 if xy equal to 0, 0. Okay, and let me try to check what is fx at 0, 0. By the definition of partial derivative, this is limit h going to 0, f of h0 minus f of 0, 0 divided by h. Now what is f of h0? Look at the definition of the function. If either x or y is 0, then f is 0. So f of h0 is 0, f of 0, 0 by definition is 0. So this is 0. The limit exists and the limit is 0. Suppose now I look at fy at 0, 0. I write this as limit h going to 0. Now f of 0h minus f of 0, 0 divided by h. This again, if you look at the definition of the function, this also is 0. So the partial derivatives exist. So can this be an alternate of derivative? That is the question. The answer is no, simply because we have already seen that the function which we are looking at is not continuous. We expect that if a function is differentiable at a point, then the function should be at least continuous at that point. But here I see that the partial derivatives exist, but the function is not continuous. So this cannot be an alternative for derivative. That is very clear. But we will see later it's not entirely an useless exercise to look at partial derivatives. It helps us to reach up to the derivative. Now, there are different ways of generalizing. I can look at something called directional derivative. So what is a directional derivative? Here the derivatives are actually looking at the difference quotients, where in the numerator you give an increment to the function. The directional derivative means in which direction you give the increment. So we start with a unit vector, let us say u1, u2. This is a unit vector E naught 2. That is, the norm of this is 1, square root of u1 square plus u2 square is equal to 1. And I call this u. Then I define, given a point x naught y naught, I define duf. This stands for the directional derivative in the direction of u at x naught y naught to be limit h going to 0 f of x naught y naught plus h u1 h u2 minus f of x naught y naught divided by h. Using the rule of addition in R2, I write it as limit h going to 0 f of x naught plus h u1 y naught plus h u2 minus f of x naught y naught divided by h. Okay. Now, if this limit exists, then I call that the directional derivative of f in the direction u exists. Now, if you choose u to be equal to 1, 0, then what is du f at x naught y naught? By the definition, it is limit h going to 0. Now, f of x naught plus h I get, because u1 is 1 but u2 is 0, so I just get y naught here, minus f of x naught y naught divided by h. And this is a known quantity, we have seen it. This is nothing but fx at x naught y naught. So the partial derivative del f del x is nothing but the directional derivative in the direction of the vector 1, 0. Similarly, you can check that if u is equal to 0, 1, then du f at x naught y naught is nothing but fy at x naught y naught. Okay. Now the question we ask is, does existence of all directional derivatives imply continuity of the function? So this is the question. Does existence of all directional derivatives imply continuity of the function? Well, the answer to this question is no. That can be shown by the following example. Let us look at this function. F of xy equals to xy square divided by x square plus y to the power 4. If xy is not the origin, it is 0 if xy is equal to 0, 0. Now I am going to check that f is not continuous at the origin. So what I do is I approach 0, 0 through the path x equal to my square. If I do that, then f of my square y, that turns out to be my square times y square, that is m y to the power 4 divided by x square now means m square y to the power 4 plus y to the power 4, which is m by 1 plus m square. So if I take limit y going to 0, it is anyway m by 1 plus y square. It does not depend on y, and the limit depends on m. So if I go through different paths, I get different limits. So this implies f is not continuous at 0, 0. But then what about the reductional derivatives? First note that the usual partial derivatives exist, because limit h going to 0, f of h0 minus f of 0, 0 divided by h turns out to be equal to 0, because f of h0 is anyway 0, follows from the definition of the function. So is f of 0, 0. So this quotient is always 0. Hence the limit is also 0. Similarly, limit h going to 0, f of 0h minus f of 0, 0 divided by h, that is also 0, because f of 0h is 0, and so is f of 0, 0. Now the question is about other directional derivatives. So let me choose a vector u1, u2 such that u1 not equal to 0 and u2 not equal to 0. Because if one of them is 0, that case I have already taken care of in the usual partial derivatives. Now we look at the limit h going to 0, f of t u1 u2 minus f of 0, 0 divided by h. This is same as limit h going to 0, f of t u1 t u2 minus f of 0, 0, which I know is 0. Sorry, this is, instead of t, it should be h. Instead of t here, I have h, because the increment is given in terms of h, divided by h. Now I just write down the definition of the function. This is limit h going to 0. Now x y square, that means h u1 into h square u2 square divided by x square, that means h square u1 square plus y to the power 4, that means h to the power 4 u2 to the power 4, but then there is an 1 by h, so that sits here. If I calculate, what I get is limit h going to 0 u1 u2 square, because in the numerator I have an h cube which cancels with the denominator. I get u1 square plus h u2 to the power 4. That limit certainly is u1 u2 square divided by u1 square, that is u2 square by u1. So the limit exists, and it certainly makes sense, as I have chosen my u1 u2 both to be not equal to 0. So you see that directional derivatives exist in the direction of any vector, but at the same time we have proved that the function is not continuous. So existence of all directional derivatives can never be a replacement of existence of derivatives. So in the next lecture we are going to see how to define derivative of a function of two variables.